Okay, hello everyone. In our last class, we have been discussed in detail about derivation of Lagrange equation from D'Alembert principle. In detail, we have been discussed. Okay, and we found in case of conservative system, the Lagrange equation is represented by d by dt of del L by del Qk dot minus del L by del Qk equal to 0. Here, Qk is your generalized coordinate and L is called Lagrangian of the system. And L is nothing but kinetic energy T minus potential energy U of the system. This T is nothing but kinetic energy, U is nothing but potential energy of the system. In case of non-conservative system, the Lagrange equation also found in same format d by dt of del L by del Qk dot minus del L by del Qk equal to 0. But here in case of non-conservative system, Qk, which is generalized force, is represented as minus del u by del Qk plus d by dt of del u by del Qk dot. Whereas in case of conservative system, Qk dot, the force component or generalized force, is represented by only the gradient of negative gradient of potential minus del u by del Qk. This is the difference between the conservative and non-conservative system that we discussed in our last class in detail. But here you can found in equation number 13, which is belongs to your non-conservative system, and this one non-conservative system 15, both are in same format. वो दोनों same format में है. तो in general, Lagrange equation of a dynamic system is this one, d by dt of del L by del Qk dot minus del L by del Qk equal to 0. Just remember this one, because in this class, from this class, we are going to start to discuss application of Lagrange equation. First, we are going to discuss in this class, we are going to discuss equation of motion or finding the equation of motion of one dimensional linear harmonic oscillator. Okay, so I suggest to all of you that you just remember this general equation number 15, that is your d by dt of del L by del Qk dot minus del L by del Qk equal to 0, which is called as your Lagrangian equations, where Qk represents the generalized coordinates, Qk dot represents the generalized velocities of the system, L represents the Lagrangian of the system, which is nothing but T minus U, where T is your kinetic energy, U is the potential energy. Now consider our today's discussion, today's problem, that we have to find out equation of motion of 1D dimensional linear harmonic oscillator. Here you can see this is a spring system. Here this is spring system, a object or mass moving to and fro about its mean position. O is the mean position, about its mean position it is to and motion is the to and fro. And so this figure represents the one dimensional harmonic oscillator. Okay, for this one dimensional harmonic oscillator, whenever we have to find out the equation of motion using Lagrange equations, then we have to find out the generalized coordinates, okay, generalized velocities, and corresponding Lagrangians, that is your L equal to T minus U, where T is your kinetic energy, U is the potential energy. Here in this case, as this object moves to and fro about its mean position along x-axis only, so generalized coordinate is only one. That means your Qy is your x only. So generalized velocity, if I am going to consider Qy dot, is also one, that is your x dot. Along x-axis it has displacement, and along x-axis it has only velocity. Okay, again, to find the equation of motion, we need kinetic energy of this system and potential energy of this system for corresponding generalized coordinate and generalized velocities. Here generalized coordinate is x and x dash is the generalized velocity. Corresponding kinetic energy and potential energy we have to determine first, then we are going to go for to to find the equation of motion. Okay. So here I'm going to show you the animation of linear harmonic oscillator. This is the typical one dimensional linear harmonic oscillator example. So when a object is dragged towards positive x-axis direction, this is a positive x-axis direction, then with a force dragged towards positive x-axis direction with a force. This is so-called applied force. At the meantime, the restoring force induced inside this spring just opposite to the applied force. This is the restoring force. In this case, restoring force is directly proportional to displacement. So as much I have to drag towards positive x-axis direction, that much amount of restoring force will induce inside this spring. So it is directly proportional. However, this restoring force direction is opposite, so it is minus. So restoring force is proportional with minus displacement of the object for a 1D harmonic oscillator here. Okay, so that implies restoring force is equal to minus kx. This is the restoring force value magnitude. Right now, suppose we are going to consider this is the small displacement displaced by this object with the time t. So the velocity will be how much? Velocity, we can write dx by dt. In this classical dynamics, always velocity will be written in this format, x dot. Okay, so here x dot or velocity is your dx by dt. Now kinetic energy of the system, first we have to write the kinetic energy is your half mv square. Mv square, half m, instead of v what we have to write, x dot square. So this is the kinetic energy of the system. Now we have to find out the potential energy. Kinetic energy means t. Okay, now we have to determine the potential energy. Potential energy, capital U. Okay, here for a small distance dx, the potential energy du will be equal to what? The force is a restoring force dot dx. Here restoring force and displacement both are opposite with each other, so it will be dot product will be restoring force into dx into cos 180 degree. The value will be minus f restoring force into dx. So du will be equal to minus restoring force value is how much? Minus kx. We just put minus kx into dx. So here we found kx dx. Now total energy will be stored for the full displacement 0 to b. Suppose this is the distance x, this is the mean position, 0 position from 0 to b. How much? The integration of du or 0 to x kx dx. So this will be k is the constant taken outside of this integration. Integration of x is your x square by 2. Limit is your 0 to x. So finally we found potential energy of this system one dimensional harmonic oscillator is your half kx square. So kinetic energy of this system is your half mx dot square. Potential energy is your half kx square. So the derivation of potential energy half kx square, I am not going to write for the note for your exam purpose. You can write this derivation in your note. Okay, now we have to derive the equation of motion. Okay. So here this figure, the figure represents, I'm writing the notes for your exam only. The figure represents the figure represents the 1D linear harmonic oscillator, right? M is the mass of the object moving along x-axis, which is moving along x-axis. Okay, okay. For this case, the kinetic energy, for this case, or for this dynamics, we have to write for this dynamics, for this dynamics, the kinetic energy equal to T equal to half mx dot square. The potential energy equal to capital U equal to half k x square, half k x square. So here we found kinetic energy and potential energy. The generalized, here the generalized coordinate is only one. Here the generalized coordinate is x only, x axis only. Okay, hence the Lagrange equation of this system will be, hence the Lagrange equation, not equations, because along x axis only, so only one equation we can found. Equation will be what? D by dt of del L by del x dot. Okay, here generalized coordinate is your x only, minus del L by del x equal to 0. Let this is your equation number 1. Right, right. Now we have to find out L, and here L is nothing but your what? Lagrangian of the system. L is your Lagrangian of the system. That implies L is equal to how much? T minus U, which is equal to half m x dot square minus half k x square. Let this is your equation number 2. Okay, okay. Now to find the Lagrange equation, we have to find out what? Del L by del x dot and del L by del x. Okay, so to find the Lagrange equation, first we have to determine del L by del x dot. Now del L by del x dot will be how much? Here del by del x dot of what? Half m x dot square minus half k x square. So this term not contain the x dot square, x dot term, so obviously it will be 0. So we can found here half m x dot square derivative with respect to x dot will be 2x dot minus 0. So that implies we found del L by del x dot equal to how much? M x dot. Okay, let this is your equation number 3. Let this is your equation number 3. Put it inside the box. Equation number 3. Now we have to find out del L by del x. Del L by del x. Directly I am going to write here. Here L is the value is half m x dot square. This term not contains the x term. So del L by del x of this term will be 0, and del L by del x of this term will be how much? Minus half k into 2x. We found minus kx. So that implies what we found? Del L by del x equal to minus kx. Put it in a box. Let this is your equation number 4. This is your equation number 4. Now substitute equation number 3 and 4 in equation number 2. Sorry, in equation number 1. Finally we can get the equation, final equation. Now substitute substitute equation 3 and 4 in equation number 1, we get, say this is the note, no need to prepare your note, you just download this PDF. I'm going to upload this PDF, you just download and prepare for your exam. We get what here, equation number 1 is what, d by dt of del L by del x dot minus del L by del x equal to 0. Same thing we have to write, d by dt of del L by del x dot, how much we found, mx dot, minus del L by del x, how much we found, minus kx equal to 0. Okay, okay. So that implies here d by dt of mx dot will be how much, mx double dot minus minus plus, it will be kx equal to 0. See how this d by dt of mx dot will be mx double dot here. If you are going to apply the product rule, then it will be m derivative with respect to t of x dot plus x dot derivative with respect to t of m. So this is the constant, this value will be 0 and this will be x double dot, so mx double dot, right? Right. Now let us consider, this is your equation number 5. Actually this equation number 5 is nothing but your equation of equation motion of 1D linear harmonic oscillator, this one. This is the equation 5, represents equation of motion of motion of 1D linear harmonic oscillator. Okay, now we are going to just modify this equation number 5 somewhat here. That implies here this equation can be written in this format also, x double dot plus m divided with each term k by m, x equal to 0. Let this is your equation number 6. Okay, may you remember already we have been discussed in our core 2 that simple harmonic differential equation, but we know here, right, just right, but we know differential equation of a simple harmonic motion is like this, x double dot plus omega square is the frequency of the simple harmonic motion, x equal to 0. If we are going to consider a simple harmonic motion along x axis, then the equation we found like this, already we discussed in our core 2. Now we just compare this equation number 7 and equation number 6. By comparing equation number 6 and 7, we get, see both the equations are in the same format, both first term both are same, second term also same, right, RHS also same. That means omega square equal to k by m. That implies omega equal to k by m root over. Okay, omega is the angular frequency. This omega can be written as 2 pi by t. 2 pi by t, t the time period of the oscillation, by k by m root over. That implies time period will be equal to how much, 2 pi m by k root over. You just remember this one, this expression you just remember. Also this expression I suggest also you have to remember, because many times you can you have to use this omega equal to k by m root over, time period equal to pi m by k root over. If you remember this one, automatically you can remember this one. Okay, so here we found the equation of motion of one dimensional harmonic oscillator is represented by equation number 5. Okay, or equation number 6, Okay, so this is all about your equation of motion of one dimensional harmonic oscillator by using Lagrange equation. Okay, okay. In our next class we are going to discuss another application, equation of motion of freely falling particle under gravity. Freely falling particle under gravity. Okay, okay. Okay, here I suggest that this is enough note for your exam. You just download this PDF. I'll upload this PDF and prepare for your exam. Here I directly written the potential energy equal to half kx square. Somewhere see here, it is written here. We found k equal to, here k by m is equal to omega square. Here we found omega square equal to k by m. Instead of k, we can write m omega square. Some books it is written that half, instead of k, m omega square x square. Okay, now it is not needed. You just write k x square. And how this potential energy value is half k x square, that I have been derived over here. May you can write in the note. Okay, no need for the examination point of view, but in your note I suggest that you just write these things for your better understanding. Okay, thank you so much for watching this video. Thank you.